Hello and welcome to this month, April 2025 monthly safety training. This is your safety instructor, Jonathan Greiner. This month we're going to be covering two topics, H₂S awareness and respiratory protection. We're going to be covering 10 parts per million, permissible exposure limit, 100 parts per million, IDLH, immediately dangerous to life and health, and 1,000 parts per million, which is GTXO. Get the heck out. So with that, and without further ado, let's get this safety started. So we're going to jump right into it this month. We have about 8 different sections to this training, so it's pretty involved, but we're going to keep it pretty smooth, straightforward, nothing crazy, overly complicated. So we're going to introduce H₂S, talk about it a little bit as a chemical, what happens if you're exposed to it. We're going to talk about engineering controls, which is kind of the most common way that we control H₂S. We're going to talk a little bit about contingency plans, how to eliminate it completely, talk about PPE a little bit, and then lastly, which feeds right into that, is respiratory protection and fit testing, important parts of an H₂S awareness and management program. So let me start by introducing you to hydrogen sulfide. Most of you have taken this class before. If you've been in the oil field more than 1 year, it's likely you've taken it every single year, if not more, since you began in the oil and gas industry, the energy industry, the paper mill industry, the industry. Lots of industries talk about hydrogen sulfide. So I'm hopefully going to share a little bit more than what you typically learn in just your standard class, because we can, and I think it's important to understand what hydrogen sulfide is at its core, and not just that it can hurt you or harm you. So it is used by plants as food during photosynthesis. So it's not an uncommon thing. It returns sulfur to its natural form. It's created when the positive atoms of hydrogen touch or bond with the negative structure of sulfur. They have to make contact in order to bond. They bond quickly, they bond naturally. It's also used by us and animals to protect the stomach lining from harmful acids. So it's actually a part of our genetic makeup. Whenever we digest food, hydrogen sulfide is there to help. Hydrogen bonds with sulfur underground as well and is present in all crude oil. It's not a question of if there's hydrogen sulfide. The question is, how much of it is there? It's also found in the air, more commonly in urban areas, and it's typically found in the parts per billion, so extremely small amounts, but it's still there. When high concentrations are absorbed by the atmosphere, it also transforms into sulfuric acid, which is known as H₂SO4, and is also known as acid rain. Haven't heard a lot about this since the 80s. When I grew up in the 80s, they talked about it a lot. There were songs about it. It was a big thing. We don't hear about it so much, but that's what happens. When enough of it hits the oxygen and is absorbed by the atmosphere, you get acid rain. Some synonyms of hydrogen sulfide. This is an important part of this. Not everyone calls it H₂S or hydrogen sulfide. Sometimes it's known as sour gas, rotten egg gas, sulfane, sewer gas, swamp gas, sulfurated hydrogen, sulfurated hydrogen, hydrosulfuric acid, and H₂S. These are all kind of the synonyms, but most commonly in our world, it's known as H₂S or hydrogen sulfide. In Espanol, it's disulfur hidride, sulfur, ore, hidrógeno, gas venenoso, and hidrógeno sulfato. For all you Spanish speakers out there. Natural sources of H₂S, again, it occurs naturally. It's in swamps. It's in bogs. It's very commonly found in low oxygen environments and where you have sources of polluted water. It's a component of natural gas, crude oil, volcanic gases, sulfuric springs, and deposits as well. So it's really anywhere where you're having decomposing material, you're going to have some amount of H₂S. Again, it's not is it there, it's how much is there. That's what we're really concerned about. So industrial sources, typically we're going to see it when raw material or produced materials have a byproduct or a waste product. Typically that's where we're going to see H₂S. That can be airborne, or it can be solid, or it can be liquid. Just depends on what we're doing. Our industry, as well as agriculture, manufacturing, sewage, landfills, excavation and trenching, all have H₂S. And again, in our industry, it's not just upstream, it's also midstream and downstream in refineries where we see H₂S. And all industries have the potential to be affected by it, particularly when they have enclosed facilities, confined spaces, or piping that can contain the substance. Empty containers that once held substances, such as crude oil, can also pose a risk where hydrogen sulfide may be present. Physical properties of H₂S. We'll get into this a little bit. So it is known as an inorganic sulfide. However, it can be organic as well if it comes from bacteria. So it's highly toxic. It's colorless. You cannot see it. It has an odor similar to rotten eggs. However, you're only going to smell it in extremely low quantities. So parts per billion to very low parts per million is where you're going to smell it. We'll talk about that in a little bit. It's also extremely flammable. More flammable than propane, more flammable than methane, and we'll talk about how exactly that works as well here shortly. So it's measured in parts per million, as I mentioned. It can also be measured in percentages, typically when it gets over 10,000, because 10,000 parts is considered 1%. Grains and pounds are also ways that we measure parts per million, typically in liquid when we use grains and pounds. Most commonly in our world, it's ppm or percentages. That's where we see it, that's how we identify it. So to visualize it, I use milk here and some I use oil, but essentially it's like comparing 1 drop to 14 gallons. That's 1 part per million. 14 gallons, just take a second, think about dumping out milk, right? Take a gallon, open it up, turn it upside down. How long does it take you to empty 14 gallons? It's going to be a minute versus just a drop. Stick your finger in the top of a gallon of milk, dip it in there, boom, you have 1 drop. You're talking, it's almost impossible for the mind to really fathom 1 to a million. I mean, we talk about it all the time, but really 1 to a million, significant difference. So in terms of time, it'd be like comparing a minute to 2 years. In seconds, 1 second to 11.5 days, you're talking big numbers here, just huge numbers. So 1 part per million isn't very much. And especially when we start talking about your monitor going off at 10 parts per million, it's really not that much. So if you consult your average safety data sheet, you're going to see this grouping of information. Not necessarily presented like this, but you're going to see this. So it has a combustibility. As H₂S burns, it's going to create SO2, which you can even travel long distances in order to do that, particularly because of its density. So its auto ignition temperature, basically if you hit 500 degrees, H₂S is going to ignite. Its flash point is negative 76 degrees, meaning don't need a high temperature in the air for it to spark. Really, if you have any sort of spark, even static electricity, you can have an ignition of hydrogen sulfide. Melting point, again, this is in its solid form. It's going to melt at 117 degrees. Flammable limit concentration. This is where we get flammability. And again, we're going to dive into this a little bit deeper later, but 4.3% to 46%, this gas is flammable. So there are some schools of thought that say you could use an LEL detector as a precursor to H₂S, because if you have LEL to some extent, before you're going to get to 10 parts per million of H₂S in a gas stream, you're going to see 10% of the flammability limit before that. But anyway, that's super geeky, nerdy safety stuff, so we're not going to go super deep into that. What I do want you to know is that vapor density of H₂S is 1.19, meaning it's almost 20% heavier than air. When H₂S comes out of any sort of vessel or anything, it will separate itself from the carrier gas of the propanes and the methanes and ethanes and the xylenes and the benzene and the butanes. It's gonna separate itself and it's gonna go down. That's where we're gonna see it. Now, how much do you need for that to happen? A significant amount. It's not a small amount here. We're talking about significant amounts, and particularly when we don't have enough wind to disperse it. So non-windy days, important. We're going to talk about wind direction later, but that's really where we have to be concerned, not just about H₂S, but about H₂S and other gases as well. It's also soluble in water. Again, hydrogen sulfide, H₂S, and H₂O. They have similar common elements, so they're going to bond together easily, particularly because of that hydrogen. Visualizing this flammability. So I have a much more lengthy chart, but in the interest of time, I'm giving you the small one today. So H₂S is flammable from 4.3% to 46%. Most gases are flammable at about 4%. That's common. Propane's one of them. Gasoline is one of them. The difference is they stop being flammable, meaning the mixture becomes too rich to burn at about 14%. Between 12 and 14 is your typical point where it's like, hey, if you have 14% gasoline mixed in, say, a room, right? You have a small room where I'm recording this. It's a small room, about 10 by 10. If I were to fill, 14% of this of propane or gasoline vapor, and I try to light a match, nothing's going to happen. I might pass out. Probably won't be able to do that because there's not enough oxygen in the room either, but nothing's going to happen. H₂S, you can keep filling that room and keep filling that room and keep filling that room to 46%, almost half of the volume by air, and a match will still, or static electricity, will still ignite that gas. Now, the danger of this is that if H₂S ignites, it can ignite other gases. So it has that extremely low flash point, extremely high UEL of 46%. So even if the other gases are too rich to burn, once H₂S gets going, it can ignite other gases. And that's when you're going to get those explosion. Basically, it's going to try to find oxygen. It's going to pull it in. You're going to get explosive atmosphere. So that's kind of the issue. One benefit of H₂S and SO2, its byproduct when it's burned, is wind disperses it very quickly. So there's something they use to determine if there was a leak of H₂S, let's say from a wellhead or a tank or a treater. And what they do is they determine, okay, how much pressure is behind it, how much volume of gas, and based on wind speeds, how far would there be dangerous levels of H₂S? And with 10 miles per hour, even if that H₂S is coming off high, like at a high altitude, like from a flare stack or something like that, it disperses extremely quickly. You need to have a lot of pressure and extremely high levels for it to get more than 200 or 300 feet. For it to last a mile or so, you're talking almost unrealistic scenarios. So wind is our best friend. Conversely, with no wind, how far can H₂S impact and have particularly a deadly impact when it's concentrated? And that area becomes much larger. So again, wind is our best friend, but without wind, we're in trouble. So its reactivities, it does not like bleach, it does not like peroxide, and it does not like acids, particularly hydrochloric. Now, you may be thinking to yourself, depending on what you do, hey, we use hydrochloric acid or bleach in well treatments, and you would be right. And so when doing acid jobs, for example, knowing the H₂S level is extremely important because you can create an extremely volatile atmosphere or volatile solution, particularly downhole, if you don't know the H₂S levels. And in those cases, we have to find alternative methods for essentially cleaning the well out. We can't use just your typical hydrochloric acid, even though that's very available to us up here in the industry. So it does transform, as I mentioned. Fire will transform it into SO2. Oxygen, particularly high levels of oxygen, particularly when we have moisture in oxygen, you're going to find H₂SO4. I talked about acid rain before. In significantly high concentrations, you're going to get battery acid or sulfuric acid. So, if you've ever got battery acid on your skin, you have had an experience with highly concentrated, oxygenated H₂S. When in contact with iron, the hydrogen bonds from the hydrogen sulfide with the hydrogen in the metal. So a higher hydrogen content typically means a harder metal. So iron, steel, as you get softer metals such as stainless steel and nickel and materials like that, there's less hydrogen in the metal, therefore the bond doesn't happen, and it's a better metal to use around H₂S. But it still can be embrittled. But when that hydrogen bonds with the iron, it cancels out, and what's left is iron and sulfur. And iron sulfide is a pyrophoric, meaning it will ignite spontaneously when introduced to oxygen. So yeah, this is a ninja gas, ladies and gentlemen. This is a gas that will find 50 different ways to transform and change to create a toxic, flammable, or explosive atmosphere. So just keep that in mind. Now, I'm not trying to scare you. I'm just telling you that with uncontrolled, this is a very dangerous thing. So we're going to be talking about controls a lot here for the rest of the presentation. So I've already talked a little about metal corrosion here. It does create hydrogen embrittlement. As the hydrogen becomes less present in the metal, it doesn't hold together as well. So it gets thinner and thinner and thinner. Eventually, it will eat through welds. It will eat through the metal itself. You'll get a paper-like metal over time, just like rust. I mean, it is an oxidization essentially at a deeper level, really at an atomic level. So yeah, it's bad for metal. So typically tanks are lined for this reason, as well as salt and other things. But tank liners, anything that's polyethylene, etc., that will prevent the hydrogen from the metal from interacting with the hydrogen in the hydrogen sulfide. So there is a really good image here I like to show, which is essentially how it affects the body. So when you breathe it in, typically that's going to be the exposure route, is through inhalation of a gas, and a carrier gas that contains H₂S. What happens is our body doesn't instantly reject it like it does. Let's say you walk into an ammonia. There's very little, if any, ammonia in your body. So when you walk into a cloud of ammonia, boom, your body's like, whoa, dude, stop. Don't move any further. The reason your body doesn't do that with hydrogen sulfide is it's a known element. It's something that is in our body. The problem is that sulfuric acid at that level, we're talking about the part per million, it enters into our body, it goes directly to the nervous system, and it starts to shut it down. So the first thing it shuts down in the nervous system is the olfactory system, or the smell that human beings have, shuts her down. Then it goes after muscles, then it eventually goes after lungs, and once the lungs are impacted, the problem is the lungs are smart. They know there's a problem, so the lungs start just sending us fluid just to the lungs to protect it, right? Just like dust. If you get dust in your lungs, start sending you mucus to protect and carry that dust out, then you hack it up and your lungs are clear. H₂S, there's no irritant, there's no actual physical structure. It's actually in the lining of your lungs itself. It goes into the organ. So it's just sending you fluid for nothing, and it keeps sending you fluid until it's gone. Well, it's not going away, and it keeps sending you fluid until it does go away. So essentially you get something called pulmonary edema. Fills your lungs full of fluid. At the same time, your central nervous system is trying to shut your lungs down, because at a basic crocodile element, it knows that your breathing is making you sick. So it's stopping your breathing, sending you fluid to your lungs, and typically this is the initial, or the main reason for the fatality, is lack of oxygen in the bloodstream. And it also attacks oxygen in the bloodstream. I mean, you're talking so many crazy things can happen to your body when you inhale hydrogen sulfide. Not a good thing. So beyond that, everybody has a unique individual susceptibility to this gas. So think of it like alcohol. If you drink a beer, you may just be wasted. Just imagine you're a safety guy from North Dakota who doesn't have any friends who invite him to the bar. And one lucky day, he gets invited to the bar. First time he has a Miller Lite, he's like under the table. He just can't hang, right? So that's like the individual susceptibility to H₂S. Some people, just a little bit, knocks them down. They're done. Other people have a higher susceptibility. But I do want to make note here that everybody within, this is, if you're talking the difference between like 10 and 40 parts per million, so still infinitesimal numbers. Yet, some people have a higher susceptibility and smaller amounts can affect them. If you have a low blood oxygen content because of drinking, mentioning alcohol, then it will impact you more. If you are a smoker and you have less, again, oxygen in your blood, it will affect you more. If you have psychiatric problems for whatever reason, if you have depression, if you have anxiety, anything that depletes the oxygen level in your blood will make you more susceptible to H₂S. I don't know why, it's just the way it works. So acute exposure to it, I already talked about the lungs, I already talked about the olfactory system and the central nervous system. Essentially, the central nervous system controls everything. It tells you to run, tells you where to run, activates the muscles, again, activates the lungs, activates the hypothalamus. It says, hey, this is not a good situation to be in. So once those things start shutting down, that's where people get in trouble, particularly if they're inside of a confined space. You may think, oh, I just jump out and run real quick. That's if your mind could cognitively decide that that's the right decision to make, but a lot of times your mind is not capable of perceiving that. Imagine if you close your eyes and you can't see anymore, which way would you run, right? But it's like your mind, it's closing its eyes. And that's kind of the danger of acute and high levels of exposure to H₂S. Signs and symptoms if you've been exposed. Obviously, if you pass out, you've been affected by H₂S, but there's other signs before you hit that level. So we talked about 10 parts per million. That's where your monitor starts going off. That's essentially the safe to danger zone. Like, hey, you're not in trouble yet, but like you're going that direction. Once we hit 100 parts per million, that's where we start to see impact, to potentially lifelong impact to the body. And then over 1,000 parts per million, it's GTXO, get out, because if you don't, like, that's fatal. That's it. That's the end. And again, that range between 100 and 1,000 is where the susceptibility really starts to take an impact. So smaller amounts, let's say 15 parts per million, for example. The CDC and NIOSH says that dizziness is where you start to feel, at about 15 parts per million, you start to get confused. Headaches are common. Eye irritation, because again, if it hits your eyes, you have sulfuric acid, airborne, atmospheric sulfuric acid making contact with the mucous membranes in your eyes. Not good for the eyes. You're going to see irritation of the respiratory tract, euphorial excitement. Oddly, your body and your mind give you a sense of euphoria. Sensitivity to light, diarrhea, staggering gait, meaning, your central nervous system isn't working right, so you're walking funny. And again, we talked about pulmonary edema. I'm not going to go into that again. And then, unfortunately, chronic exposure or high concentrations, even minimal high concentration exposure, can lead to brain damage, coma, respiratory arrest, and then finally cardiac arrest. So lots of negative things happen when you're exposed to H₂S. Chronic exposure, basically all those symptoms I just mentioned, but then again, lower white blood cell count, silicosis in cancer, lungs and kidneys, just kind of like silica sand does to you. It just shuts things down. The body does not have a system like it does for alcohol, where it just, filters it through your liver and, you're good to go if you drink enough water and give it enough time. The body doesn't have a system for hydrogen sulfide like that. It just messes you up. Just imagine acid going through your bloodstream. That's essentially what it is. So some chronic exposure symptoms and signs you're going to notice. It's actually a lot like the flu and even COVID, and I hate to even say COVID anymore. I'm just tired of hearing of it, but the symptoms are not, when your body's sick, it only has so many different ways of telling you, right? Runny nose, fatigue, some digestive issues do accompany H₂S. So again, like the flu and unlike COVID, but it does have respiratory issues. You're going to have dizziness. Insomnia is pretty common. Acute sensitivity to light, weight loss. Just so many different similar things. Even cold sweats are pretty common. So concentrations and symptoms, I already talked about this. So kind of getting a little bit more granular. So from 0.01 to 1.5, this is where we can smell it. So again, if you're smelling it, that means you're on the very edge of the cloud, right? So there's a source somewhere that, and it could be miles and miles and miles away when you smell it. There's a source somewhere where you're smelling just the parts per billion here. That's where you're smelling it, to the very low parts per million. From 2 to 5, that's where, particularly if you're super susceptible, you're going to start to experience nausea and things like that. At 20 parts per million, fatigue, loss of appetite, irritability, dizziness, headache, poor memory, irritated and inflamed airways after 1 hour exposure. This is what we're starting to see. 30 parts per million, this is where, if you can still smell it, you're not going to smell the rotten eggs anymore. You're going to smell almost like a benzene type smell, which is a little bit sweet, or sickeningly sweet. And then 50 to 100 parts per million, that's where we're going to start to see digestive issues. And after 1 hour, we're going to have conjunctivitis and respiratory tract irritation. There's really going to be some issues. You're not going to pass out usually at this point, but you're going to feel real sick, just real weird. As we get above that, 100 to 200 parts per million, loss of smell completely, drowsiness after 15 to 30 minutes. Then we're going to start to see severe burning in the eyes and nose. The lungs are going to start to fill fluid. From 500 and above, you're going to start staggering. Collapsing is pretty common at this point, passing out. From 700 to 1,000, that's where unconsciousness starts to happen. And again, that's a pretty big range in some aspects, 700 to 1,000. But in another aspect, if you're talking about 1,000,000 parts, it's 700 drops versus 1,000 drops. It's literally drops in the bucket is the difference. But that's where fatalities start to happen, is between that range. And particularly if you're in a confined space, and this is where we see fatalities happen. It rarely happens just like walking across location, or even if you're near a vent, where some people do get hit, particularly truck vents. It's usually inside of a confined space, a treater building, somebody entering inside of a tank, and you can't get out. You lose consciousness. You can't breathe, you pass out, you're in the atmosphere where it has H₂S for minutes or, prolonged periods of time, and then that's when the fatality happens. So I will say this, and I think this is a good place to say it. Hopefully I've adequately described to you that regardless of your experience in the oil and gas industry, there's no amount of exposure that makes it safer for you. It's not like, oh, I was exposed to this so many times, so now I'm less susceptible. It's the opposite. The more acid runs through your bloodstream, the less susceptible you are to acid. I think we can all agree with that. If you get acid on your skin 50 times, the 51st time, it's not magically not painful. If anything, it's going to be more painful because there's less, of a base there to protect you. So 99.9% of fatalities that I've ever investigated, I don't even know if there is a 0.1%. Every single fatality I've seen with H₂S, low oxygen, SO2, any of these gases, it's because the person was not wearing their monitor. That's it. They don't wear their monitor and fatalities happen. So if you're thinking, man, this stuff's crazy, I don't know if I want to work in an industry where this is really present. I can understand that, but that's why these monitors are so important, because they tell us before we're, in real big trouble that there's an issue. So byproducts of H₂S, as I already kind of talked about, we have SO2. When it burns, particularly in high concentrations, you're going to see a bright blue flame. Not just like the base of a flame that's typically blue, it's going to be bright blue. And when that happens, you're going to get SO2. We want SO2 because even though it is as toxic, and some would even say more toxic than H₂S, you can detect it with your nose. For one, it has a real strong sulfur. It's going to burn your nostrils when you come into contact with it. Again, unlike H₂S, that's odorless. The other thing it does is it does not have flammability. That's eliminated from the equation. So even though you may have a toxic hazard, the flammable and the explosive hazard is eliminated from the equation. And so we want to burn it off if we can. So I already talked about that we can detect it, but it also is colorless, and it is also highly toxic. Again, almost as toxic as H₂S, or more so. There's like an XY coefficient and where it's more toxic and less toxic, but either way, it's bad. Let's just call it equally as bad. So as an element, sulfur dioxide, not as common as hydrogen sulfide, but it is around. It's around typically in areas where we're going to see volcanic activity, where we have large amounts of sulfur and a little bit of oxygen. That's where we're going to see SO2 come. It's also called sulfur oxide, anhydride, and sulfurous oxide. So that's what we're going to see there. So a couple things. It's also way heavier than H₂S. So like H₂S is 20% heavier than air. Sulfur dioxide is 226% heavier than air. So it's going to really love the low-lying areas. But like H₂S, a little bit of wind goes a long way. So wind is our friend. Wind direction is our friend. Calm, no wind days, not our friend. Flammable limits, it's not flammable. That's the beauty of it. It does boil if you have enough of it at 14 degrees Fahrenheit. Think about that. It's boiling below freezing. So it's an interesting deal. It does not freeze until you get to a negative 104, which is insane. And it is soluble in water. But we're typically not going to be seeing SO2 in an atmosphere where it's going to be in a solid form. It is reactive to alkali metals, ammonia, zinc, brass, copper, aluminum, and water. So it does have some reactivities to these and incompatibilities with these, just so you know. Exposure is going to be similar. It's shutting down things. The difference is our body doesn't react to it the same. Again, it's going to reject it immediately, like this isn't normal, and it's going to immediately start to shut things down, fill lungs with fluid, etc. But it's not going to. We're not going to. You couldn't continue to work in it without knowing that it's there, right? So there is a significant difference. Concentrations and symptoms, again, basically 1 to 1,000. Death's going to happen at 1,000, and again, whether it's more or less toxic is, a little bit of a debate. But you're going to smell the burn match order. You're going to start coughing heavily at 12 parts per million. You're going to have extreme irritation at 150. See, H₂S, you might not even really notice it at 150. 500 parts per million, you're going to feel a sense of suffocation. So before you hit the level of like fatality, you're already feeling like I can't breathe. Whereas H₂S does not give you that warning. Accepted exposure limits here are basically H₂S, it's 10 parts per million. For SO2, it's 2 parts per million, so much lower threshold. And we don't typically have SO2 alarms in our foregas. However, you can get them installed depending on the scenario if that would be necessary. A lot of times they're done by area monitors, but a lot of our drilling rigs now have SO2 monitors because of the recent BLM requirements that put that out there. So routes of exposure, most commonly inhalation. It hypothetically could become part of crude oil, depending on the scenario, and particularly in like spills or massive explosion events where you have a lot of material that you're cleaning up, but not typically going to be absorbed through the skin, through fluid. Could be ingested in the same manner, and then injection also could happen, but also very uncommon. IDLH. So I mentioned this as 100 parts per million. And essentially what IDLH means that we're in a range that anything above this could cause potential serious, irreversible impact to the body. This is typically where a full face piece respirator would be required, which we'll get into a little bit, such as an SCBA or an airline supplied respirator. And the difference there is does it have an airline or not? And that's pretty much the only difference. So that's at 100 parts per million for H₂S, and it's 100 parts per million for SO2. So IDLH atmospheres, some other things besides 100 parts per million would be a low oxygen atmosphere. So if it's under 19.5%, or if we don't know. So if you're like, man, I'm going to go work on this well site, there's no data regarding what, if we opened up this thief hatch, what's going to come out of there. We have to assume that is an IDLH atmosphere. You can't just be like, well, let me open up the hatch and stick my head in it and see if the monitor goes off. That's not how this works. You just think, hey, this is a IDLH atmosphere. And that is where some people have gotten in trouble, particularly if they're working alone, no monitor, or their monitor's, low on their hip or on their boot or something, and they put their head over a hatch, breathe it in, and that without the monitor working or in its proper area, we have seen fatalities that way as well. So 100 parts per million, easy number to remember. This will probably be on a quiz later. 100 parts per million is your IDLH. So I said we're going to get into the elimination and control of this, which is important, right? I mean, if we know it's there, we know it can hurt us in so many different ways. How do we control it? There's a ton of ways we control it. First of all, the wellhead. That's the first way we control it. We control the flow of liquid and natural gas in a closed loop system, typically to the treater and then to the tanks. We control it, right? And any excess gas would go to the flare, which would be burnt nowadays, particularly nowadays, 20, 50, 100 feet in the air, depending on the size of your flare, well away from the working areas. Now, where it gets tricky is when we break into the process, when we open up a hatch, when we dink around to the Kimray, when we vent off of our truck, where we open up to the tank, offload or onload, and we have a truck that's venting. That's where we're going to have exposure. So that's where we're really going to talk about elimination, substitution, and engineering controls. Then you have signage, hey, H₂S may be present at windsock. That's what we consider administrative controls. And then lastly, at the very, very bottom, the smallest layer of protection, the peak low point is PPE. That's the last thing we do. We do everything else before we don the SCBA, essentially. So engineering controls, the main method we use is flaring, right? If you have excess gas, particularly over 8 to 10 ounces, that's going to be pushed out through the flare or into a pipeline, depending on, the makeup of that specific well's infrastructure. So we flare it, particularly high levels of H₂S, and that's going to burn off. It's going to create SO2, and a good amount of wind, or even the pressure from the gas itself, can push that H₂S far, far away. And again, that depends on the geology, or the geography rather, of where we're at. If we're in a low-lying area like a bowl, if you're up in the breaks in like a bowl valley kind of well site, and there's high levels of H₂S, you're going to see some things. You're going to see tanks that are rotted out. You're going to see rust on everything. You may see dead birds or dead cows or just, a general sense of dead vegetation. Not like not present vegetation or dried out vegetation, like sick. That's what you're going to see because plants and animals cannot handle high amounts of hydrogen sulfide. So flaring is number one. That's how we eliminate H₂S, by putting that flare high up in the air, burning it off, and letting the wind disperse of it appropriately. Administrative controls, I already mentioned. Permits and JSAs are other methods. How are we going to work around it? We're going to stay upwind, crosswind. These are considered administrative or, to some extent, engineering operational controls. Safety meetings, talking about them, training like this, signage, safe work practices, rotation of workers, equipment inspections, and again, keeping everything in the process as much as possible. These are all administrative controls. So some safe work practices here, we already talked about it. Staying upwind, following permits, having CPR, training so we're ready, having standby personnel around, not working alone in high levels of H₂S and high H₂S environments, having appropriate PPE and supplied air equipment on standby, using it as PPE, having it ready is administrative control. Staying aware of wind conditions at all times, and checking everything to make sure there's not ignition sources in the general area where vapor or other gas concentrations may be present. So some other safe work practices, making sure we're crosswind first. We hear upwind a lot, and I've even mentioned it a lot, but truly, crosswind is always better, because if I'm directly downwind from a source and I move directly upwind, I'm moving towards the source. So crosswind is typically going to be first. In fact, in our training, you'll see this in the quiz later. Again, another hint that crosswind is the first move. Lockout, tagout processes and equipment, keeping non-essential people out of the work areas, using the buddy system whenever you hit above IDLH or 100 parts per million, notifying your supervisor before starting work that could release H₂S, or if you're going onto an H₂S route or a well that contains high H₂S, particularly if you alone, letting somebody know. And then using caution signs, labels, windsocks, etc., to alert other people that, hey, you're entering an H₂S area. So importance of moving crosswind upwind. So here's, and it's just me talking here, so I'm going to pretend you're responding to me. But here we have a muster point sign in the upper left-hand side. You can see we have the windsock pointing, that's essentially upwind is where the muster point is, which is good. We have me down in the bottom right-hand corner, and we have an H₂S release coming out. So it's coming towards me. So I'm going to go crosswind first, which is the red arrow up, and then I'm going to go upwind after that. So if I go straight upwind from that current location, I'm going to walk right into the source, right at that wellhead. So I want to go kind of in a wide moving arc. You're probably not going to walk straight and then turn, left 90 degrees like a military march. You're probably going to do a wide arc, and that's perfectly acceptable. Contingency plans, another emergency, or administrative emergency. It's like, what do we do? That's really the question. What do we do? Blowout happens. We have 1,000 parts per million. What's the process? A lot of times you're going to say, oh, we got to shut the road down so people don't drive by. It's like, yep. We have to alert the neighbors. Absolutely. We have to call well control people. Definitely. We have to, there's one contingency plan in the the Bureau of Land Management, federal agency. Now, I don't care what you think about federal agencies. We're not going politics here. No dark Brandon, none of that. They say dynamite, in certain instances, is the acceptable method of controlling a well that is a blowout with H₂S. You're talking crazy, like blow some stuff up. That's sometimes preferred over letting it just, escape into the atmosphere and kill people or animals or, anything. So just keep that in mind. Immediate action plans are typically like not necessarily just a contingency plan, but like, what am I going to do immediately? And we just talked about it. Upwind, crosswind, go to the muster point. The muster point's entrance location. We're going to turn everything off. We're going to shut down trucks. We're going to close the valve. We're going to lock it out. Whatever the plan is if something unexpected that you believe could happen, worst case scenario situation, what are we going to do immediately? That's what our immediate action plan is. So first aid measures. Let's talk about if somebody does get exposed. Most important thing is fresh air. Getting them out of the immediate environment as quickly as possible into fresh air. Protecting yourself is number one. I talked earlier about statistics of people dying without monitors. I'm going to delve into that a little bit more. A lot of cases where there's multiple fatalities, so statistically high situations where there's multiple people that die. Somebody's in a confined space, such as a tank, underground vessel, something like that, where there's H₂S present. And sometimes it's like, I've heard of it I think it was in Scotland, where there was a water tank for horses that somebody went into to clean or pick something out of, and it had a lot of H₂S in it. So uncle goes in, goes down. Nephew goes in, goes down. His dad goes in, goes down. And I think the fourth person almost passed out, but was able to, keep themselves out, or they did pass out. But anyway, they didn't die. Called 911, 3 people dead in the tank. Make sure if you do go to rescue somebody, if they go down because of H₂S, or even if it's a heart attack, even if you don't know what it is, you see someone go down, you have to make sure you're protected before you go in and create a more serious scenario. So if it gets in your eyes, now again, this is small amounts, right? We're not dead. We just, hey man, I got exposed. My eyes are burning. You got to flush it for 15 minutes with an eye wash solution or saline or something that's going to essentially get as much of the surface level contamination off as you can. But again, this stuff's bad, man. It's like acid. It's not a something that's just going to wash out. Facility surveys are also really important for H₂S. This is where safety companies like Basin Safety or oil companies themselves will test their facilities on an annual basis or biannual, depending on the nature of the well, and record what the H₂S levels are at the treater, in the tanks, in the breathing zone, in the casing, sometimes the tubing, but tubing and treater are typically aligned, and there's a lot of fluid typically, so tubing is difficult. But they're going to take all these different tests, and they're going to determine what level of H₂S is at that facility, and then hopefully communicate that to you as the contractor or the employee to let you know what you may be exposed to, what you should expect. So for gas detection equipment, I talked about measuring H₂S. There's different ways. There's direct reading instruments, which are a lot like a 4-gas that we wear, but it has a pump on it with a wand. There's area monitors where you put it out, and then there's fixed monitors that are permanently installed. So area monitors are more mobile. You can put them here, move them there. Fixed monitors are just in a fixed location. A lot of times we see these inside of large treater houses or separator buildings or things like that. So a lot of different options. They're usually set at about 10 parts per million, just like our personal alarm monitors, which alerts us that we're hitting the personal exposure limit threshold. Now, make sure this is clear. Personal exposure limit is 10 parts per million. Remember, 15 parts per million, you start to get sick. So the permissible exposure limit essentially means you can work around it for 8 hours. 8 hours you can work around H₂S at 10 parts per million. I don't recommend it. That's where your alarm starts going off, and that's where you have acid around your body, and you know it. And just 5 more parts per million, you can only be around that for 15 minutes a day total over an 8-hour day. That's the max you can be around for 15 minutes. So really, any times the monitors are going off or there's any H₂S being detected at all, it's just get out. Go find out why it's in the area, figure out a way to isolate it, get rid of it entirely, close the valve, shut it in, turn it off, don't be working in it. But 10 parts per million, you have an 8-hour limit where you can be around it. So personal alarm monitors, again, can be set at 10 usually. The 4-gas monitor, in addition to H₂S, is going to have lower explosive limit, carbon monoxide, and oxygen. And again, because low oxygen levels are going to mean immediately dangerous to life and health. You need to have oxygen to breathe. So we're going to test for that just to make sure we have it. So with personal monitors, we need to make sure they're being worn in the breathing zone. They need to let us know above 10 parts per million that we're going to be exposed. Some of them go above 100 parts. Some go to 2, 3, 4, 500 parts and will still tell us. Some of them cut out way before that. Their job is just to alert you, to tell you to get out. That's it. So it is not a measurement device. Your personal monitor is not how we measure for H₂S. It's just how we detect if it's present to alert you to get out of the area. Different clients or operators may have different requirements for not just do you have a 4-gas monitor, but what's installed in the 4-gas monitor, what are the set points of the 4-gas monitor, and what does a 4-gas monitor do? Does it alert you? Does it send a satellite signal to space to let your safety guy know? Yes, those do exist. What does your 4-gas monitor do? And different customers are going to have different requirements. So fixed detectors, like I mentioned, typically going to be in or outside of buildings where we know there's a high likelihood we're going to have H₂S, and they're typically set up to some sort of facility alarm that's going to alert us, that the facility has H₂S somewhere. That's typically how they're designed. Remote monitoring systems, as I mentioned, these are meant to be picked up, moved around, placed in different areas. Typically, these are going to be downwind during some sort of, operation where we're releasing gas intentionally, knowing that it's there, and we just want to make sure that there's not, high levels of H₂S. 4-gas monitors with pump or direct reading measurements systems. These are usually what we use. Like, we'll open up a well into like a small gas collection vessel, teeny tiny little bulb, and open it real quick, close it, and then we put our direct reading measurement into that, or a ray tube, which we'll talk about in a minute, and that's going to pull just a small sample to give us a picture of what levels of H₂S that we're dealing with. These need to be bump tested. Anything that has an electronic method of testing need to be bump tested, and they need to be calibrated typically every 90 days, sometimes more often, sometimes less, but they need to be calibrated, because what will happen over time is the sensors will they'll drift. So it may be set to set off at 10, but it gets bounced around the truck. It's exposed to high or cold temperatures. It's been exposed a bunch, and then it's not going to alert you until you're at 15 or 20. Even though it's saying 10, it's really 15 or 20. So that's why we calibrate and bump test, as well as just make sure the alarm works. That's kind of what we're testing in all those different scenarios. So that pretty much wraps up the H₂S awareness portion of this presentation. Now we're going to get into respiratory protection, which is essentially our, how do you protect the lungs, man? Because if you get it in your lungs, that's the primary port of entry. If you can protect yourself through engineering controls and elimination controls, that's great. If we have to work around it, there's no other way. We're going to be talking about how to protect your lungs and your central nervous system, essentially. So medical surveillance is important, and what we're saying there is that before you wear a respirator of any kind, you need to be medically qualified. Respirators can, limit the amount of oxygen that goes into our bloodstream, and if we're susceptible to low oxygen issues such as fainting or passing out or even claustrophobia, heart issues, things like that, the medical surveillance is going to tell us that. Say, hey man, you can't wear a respirator, which kind of limits your ability to work around high hazard areas if you can't wear a respirator. So you got to take a medical evaluation. They're not every year, typically. Most people do them every year just to make sure you're good to go. But yeah, that's an extremely important primary part of a respiratory protection program. So if you ever are exposed, that's another part of the medical evaluation. Isn't just can you wear a respirator, but if you are exposed, they want to test you. They want to test your blood. They want to test your lungs. They want to test a lot of different things to see how you were affected or impacted. We talked about PPE already. We're going to get more in depth as a part of a respiratory protection program into what PPE protects us. As I mentioned, this is the last line of defense. This is you getting out. This is you rescuing somebody if you're trained where there's already a release and we've done everything we can, but it's still present. So there's some different types of respirators. There on the top left, you'll see a supplied air respirator. The little 5-minute pack is actually an SCBA with a pigtail hooked up to it. So it's supplying air. In this case, we're on top of one of those large, facility tanks, above ground storage tanks, AST, for oil, and we're installing some fall protection onto it. These guys are working up there for hours. But that SCBA is designed as a self-contained, So if the airline fails, they can disconnect the airline and get out. We have filtering respirators as well. Those do not work for H₂S, but they will work against dusts and other types of irritants and contaminants that are airborne. But hydrogen sulfide will go right through that puppy. So supplied air, like the picture before, means we have an auxiliary or separate air supply that's feeding our mask, right? And typically there's going to be a regulator to that little SCBA that's going to give us the right pressure. Because it's coming out that big tank at 2,000 PSI. You need to regulate that down first from the tank, then to your regulator and your small SCBA, and then down to typically 80 to 100 pounds of pressure is all that we want to see there. So self-contained, now it's not to your face, but to your smaller regulator, which then obviously we can even make it demand where it doesn't have any pressure. It's just giving us air when we pop the diaphragm inside. So we have self-contained breathing apparatuses. Those are the work packs, which is the little picture you saw before. And there's emergency use respirators, which are typically called EEBAs, or emergency escape respirators, and we'll look at those here. So the EEBA is on the left here. That's like bag over your head, can't seal, just gives you essentially an umbrella of air going over your face to get you the heck out. Airline respirator, a 5-minute pack, also known as an escape pack. Even though the EEBA is a true escape pack, it's also called that, just to get you out. You got 5 minutes maximum in that puppy, typically 2 minutes if somebody's running and using a lot of air, breathing hard. And then you have your rescue pack, or a work pack depending on your scenario. But that's going to typically give you between 15 and 30 minutes of air, depending again on how heavy you're breathing. So employers are responsible to have a respirator protection program, deliver and provide the medical evaluation, deliver and provide the fit testing, deliver and provide when we need to wear respirators and what methods we're using to inspect them and clean them and take care of them. It's typically going to be in your program. It's going to walk you through every possible scenario of how to clean them, how to inspect them, what types of respirator we use and why and where, etc. So monitoring it is kind of the employer's job as well. Typically the safety department is going to hold that responsibility, but are people wearing their breathing air? Are they keeping them clean? Are they, storing them properly, etc.? That's all part of monitoring the respiratory protection program. Leaving the work area, if for whatever reason your respirator gets damaged or bent or out of shape, or the seal isn't working properly, you need to leave. If you can't see because your respirator is fogged up, you need to leave. If you need to inspect something just to make sure it's working right, you need to leave. All those are times to leave the work area. Respirator cleaning, really it's after each use. I'm after and before each use guy, so I like them both. So you'll see after and then you'll see before here in a minute. All respirators need to be cleaned before and after. One thing you do not want to use to clean these is anything that has alcohol in it. Alcohol sprays, alcohol wipes. It will degrade the rubber, the soft rubber that's supposed to form fit to your face, and it will degrade them and then dry them out so that they don't seal properly. So keep that in mind. So again, before each use and after each use, water is great, doesn't hurt them at all. A little bit of Dawn dish soap doesn't hurt it at all. And some form of disinfectant also kind of highly encouraged. And then you want to make sure if you do use a cloth to dry it, that it's a lint-free cloth. So no paper towels, no lint rag. A chamois is good. That essentially has no lint, solid rag. Storing them, you want to store them in a clean, dry place. We don't like moisture because again that detracts bacteria, and we don't want them to get smashed or crushed or be exposed to sun. You want it to be clean, dry, out of the sun. Inspections, they need to be inspected again before each use, and then at minimum on an annual basis where it's recorded, and then monthly where it can be like kind of field recorded or a little bit less formally recorded. If you decide to use a respirator but it's not required, like let's say your facility, you're working around a lot of dust outside or whatever, and it's not bothering anyone else, but you're like, man, I need to wear a respirator. This dust is messing me up. Perfectly okay. But if you decide to wear your own respirator, you have to follow the respiratory requirement of OSHA if you're on the job site. So you can't just say, hey, I never clean my respirator, but I don't have to wear it, so it's cool. Nope, you still need to clean it if you're using it at work, for example. So choosing the right respirator with H₂S is easy. it needs to be air supply. You can't use a filter, right? Pretty straightforward. But because this is just general respiratory protection, we'll go a little bit more in depth here on how you pick. So there's N series, R series, and P series. They're typically going to be color coded. These are NIOSH, recommended. And then every respirator has a protection factor called an assigned protection factor built into it. So when you go to buy, a respirator, even if it's just a 3M half mask type for painting, the type of filter you buy is going to have a protection factor. The better protection factor with filters, typically the better the filter, typically the less useful life and the less airflow you're going to get pretty quickly once it's compromised. So ideal H atmospheres, mandatory full face piece air supply, period. Once we hit ideal H, which is low oxygen or some high level of contaminant, such as 100 parts per million with H₂S, again, might show up on a quiz later, then you need to have air supply. Below that, again, unlike H₂S, still you need it, but with other contaminants, there are different assigned protection factors, but you have to be below that threshold of what we consider ideal H. I already kind of went over this. SCBAs have the highest level, and then, it goes 10, 9, 8, 7, and then below. Service life is the amount of time the equipment's able to be used. Everything has a different service life. Typically, your filters are going to be the first thing to go, but some of the other equipment as well can go just based on the date it was manufactured. But then other things such as wear, tear, use, being crushed, moisture, sun, etc. If you use alcohol wipes on them, those will significantly reduce the useful life. Medical evaluations, I already kind of went into this in depth. Essentially, it's about 50 questions where they're going to ask you about, again, claustrophobia, medical conditions, heart conditions. I'm sure COVID has made its way into this questionnaire. I know I said I didn't want to say it, but I said it again. But I'm sure I haven't taken one of these in a couple of years, but I'm thinking it's probably on there. Do you have long COVID? Fit testing. This is an annual requirement, period, no matter what. Which you're going to, and then sometimes more often. Fit testing is just essentially ensuring that the respirator you're wearing seals to your face properly and doesn't leak air. So, or, that it doesn't allow contaminants past. That's really the design of a fit test. So you used to do these with smoke. We don't usually do that very much anymore. Qualitative, just not so common. You only can do this for half face masks. So we do these sometimes with the bag over the head, the whole nine, but that's kind of going away because we have quantitative fit tests. So at Basin Safety, we have these. People come in, they get the quantitative fit test. Essentially, we provide a data analysis of the seal of that mask for you, and it's in the chart. It's pretty. It's got your name, the whole nine. Repeating it again every year, or if there's significant weight gain, significant weight loss, then we're going to repeat that fit test. Also, if there's a different hazard that you're exposed to, meaning you need to use a different respirator, or if your company changes respirators from a Scott, for example, to a 3M or to an MSA, then the fit test would need to be repeated. The seal checks need to be done every time you put them on. You're going to do a positive seal check and a negative seal check every single time. This is without the filter on. If it has a filter or if you have a regulator attached to an airline supply, you're going to remove that, and then you're going to put your hand over the inlet for the filter cartridge or the regulator, and you're going to breathe in, make sure it seals, and then you're going to give it a nice little pop out. If you breathe really hard, you're going to overwhelm in the positive pressure test, but you give it a nice little puff of air and make sure that it seals and that air holds inside of the mask against your face. So the importance, probably don't need to go super in depth here. If seal ain't working, you're breathing in whatever's around you. And if it's H₂S, that can be fatal. Basin Safety, our guys are intentionally going into atmospheres and testing for hydrogen sulfide, whether it's at the well site, inside of a treater, inside of a tank, inside of a confined space, they're testing for it. So for us, a seal is like the most important thing possible. So you want to do this every single time you put it on. And if sweat or, we've seen it where the work area, somebody bumped something in their mask, bumped off. And if you're in a high danger area and that can happen, you want to make sure that your air supply is giving you positive pressure air so that even if your mask does get bumped and the seal goes away, you have air inside of the system pushing the atmosphere away from you. That's why we like the positive pressure. So standby personnel, obviously, if we're around 500 parts per million or more, we want a buddy there. I mean, period. 100 parts per million is the recommended practice, and that's where we have them, and most people are going to have them. But if over 500, one breath is fatal, or potentially fatal, why not have a buddy there? Why be working in that area by yourself? It doesn't make sense. A standby personnel is somebody in a safe zone with training and the proper equipment to rescue or to perform non-entry rescue if an emergency were to occur. And this is really the central part of it. It's the buddy system. If you're a rescuer, however, a true rescuer, you've been trained to do so. You've went through a man down exercise. You've rescued a dummy or a live person if the instructor was a jerk and they made someone get drug across the ground. We use a dummy because, sometimes I use people, but only when, I really don't like them. And then I don't tell them about the dummy. I just say, we don't have a dummy, so you're the live exercise guy. No, I don't do that. I want to, but I don't do it. So the rescuer will have done that with ropes or non-ropes or stretchers and be qualified to do so through certification. You can't just be like, hey, man, you working today? No, okay, I need a rescuer out here. Come in and get me if something goes wrong. Person needs to be trained. Person needs to be qualified. Person needs to be certified in order to rescue somebody. So that's going to be typically done in and above your IDLH atmosphere of 100 parts per million. So wrapping this puppy up just over the hour mark, H₂S is a colorless gas that is present in all industries, and as well as just decomposing material in the atmosphere and in the world itself. The action level, the alarm level for H₂S is 10 parts per million, also known as the exposure limit, the personal exposure limit. IDLH for H₂S and SO2 are both 100 parts per million. Individuals exposed to it need to be cleared by a licensed medical professional before they go back to work. So if you are exposed, even in smaller amounts, you need to go see the physician. Respiratory equipment is required in IDLH atmospheres, and a full face piece auxiliary air supply is required with H₂S or SO2 if it's over 100 parts per million. The buddy system is also required in all IDLH areas, so make sure you got a buddy out there if you're working in dangerous areas. Well, with that, we're going to go ahead and wrap up this training today. Thank you so much for paying attention and being a part of our H₂S awareness training, April 2025. You guys were excellent. Take the quiz after, leave a comment and review, go to the Google, say we did a good job, say we didn't do a great job. Love to hear from you. Thank you. And with that, let's keep this safety going.